Hello everybody, welcome back to our series. So if y'all remember last time we have planned a way to compute the exponentiate of a matrix, and we say that we'll use Taylor series by adding on the matrix term again to finally eventually come up with the exponential term. We also propose that our matrix can be smartly decomposed into a matrix P times the diagonal matrix and the P inverse. So in this next part of the video, we figure out what is P and what is D and how to compute the rest. Okay, so before we doing that, all right, let's now figure out what is P and what is D. Okay, so in order to do that, we're gonna do a little bit of manipulation first. Okay, so all right, let's do some manipulation. So what manipulation you can do? You start with A equal to P times D times P inverse, or to the power of -1. I'm gonna go ahead and do some matrix manipulation. So first I will apply both of the matrix to matrix P. Okay, so you treat the left side as like a big matrix and the right side like a big matrix. Okay, and you apply that matrix to matrix P. So AP equal to PD P -1 apply to P. Okay, and if you use matrix associative characteristic, matrix associative characteristic, you arrive at AP equal to PD apply P -1 P. So PD P -1 apply to P is same as applying matrix PD to matrix P -1 P, and I think that's the associative characteristic matrix. Okay, so that implies that apply matrix A to matrix P is equal to apply matrix PD to P -1 and P become I, right? Become, I think it's the identity matrix. So what you're left with? You're left with just D. Okay, you left with PD or P apply to D. Okay, you get to this point, and now we have a clearer pictures of what it look like. So D right here, D is diagonal matrix. Okay, of A. So it depends on how much entry A have, D will have that. So for example, your A matrix is gonna be like 1 6 7 2 4 7 3 1 1 1. So D will look something like this. D will look something like 1 2 3, and then the rest 0. Okay, so it's based on A, so we can generalize D, okay, to be lambda 1, okay, 0 0 0, 0 lambda 2 0 0, and then you have 0 0 0 lambda n. Okay, and what's on the lambda? The lambda on the lambda 1, lambda 2, lambda lambda I, and then lambda n is called the eigenvalues. Okay, so basically we come to this point, and then we finally recognize what form D look like. So D is like the collection of eigenvalues, or eigenvalues column vectors matrix. Okay, now let's find what is P. Okay, so I'm gonna make an assumption. Because if you look at our equation right now, AP equal to PD, you can say that, let me write in red. So assume P is a block matrix of column vector alpha I. Okay, so again, in order for two matrix to be equal, it has to be consistent. So why I'm assuming this? So remember, we are here right now, right? So P equal to PD. Okay, y'all remember? And A is our square matrix, right? So let's check the dimension of A. A is n times n, right? D, because it's bare, all of the eigen values belong to n, which is n. So D also have n times n. What's that? N times n's value dimension. So our P, we try to make it similar to it. So our P, we try to make it is a collection of column vector alpha I, so alpha 1, alpha 2, all the way to alpha n. Yeah, this is what we aim to be, and later we'll figure out what is alpha. This is what, let me make some notations easier for y'all. So alpha I is the column vector. Okay, so this is what we want B to be, because the dimension from left hand side and the right hand side must match. So this is what we aim P to be. Then later we can figure out what is alpha. So let's go ahead and figure out what is alpha together. Okay, so let's me like this. So from this expression right here, AP equal to PD, I can write it like this. So our A is gonna be A of alpha 1, alpha 2, alpha n, right? Just substitute in our assumption from above. And for D, I can write like this. I can write lambda 1, 2, 0, 0, lambda 2, 0, lambda 2, 0, 0, 0, 0, 0, lambda n. Okay, so D, I just basically substituting the definition and assumption we have made previously. Okay, now I'm gonna go ahead and expand these. Okay, but that will be a topic for the next video. So let's recap what we did. What we did is we do some manipulation to arrive at AP equal to PD. We say D is the diagonal matrix of A, which contains all the eigenvalues. And P, we use some manipulation and we make an assumption. We want P to have we treat P as a collection of column vector alpha. And from this point on, or in the next video, we'll figure out what's alpha. Okay? Thank you y'all for your attention, and I'll see you in the next video.